Well, good morning. The second topic in this unit in chemical reactions is balancing chemical equations. And I know this is something that you did probably in middle school for a little while, and we are going to re-hit on this topic and get a bunch of practice on balancing equations. In order to get really good at balancing equations, you just need to do a bunch of practice. So make sure you do a bunch of the homework this week that I will supply in Canvas that follows this video. Along with, I'll also give you some different interactive websites that you can log into where you can do fun balancing chemical equation games and be able to check your understanding for this concept. Okay? Now, first of all, a chemical reaction is a process in which one or more reactants are converted to one or more products. The bonds between the reactants are broken and new bonds are formed, forming new chemical compounds with different sets of properties. There's a chemical change. The substance are into something else. Again, reactants are anything that is before the arrow in a chemical equation. The arrow separates the reactants from the products. The reactants are any of the chemical substances before the arrow, and the products are the new substances that are formed from the reactants. Okay? For example, up here I've given you a reaction. It's unbalanced of hydrogen gas and chlorine gas reacting to form HCl. Conceptually, if you were asked to draw this, you would draw a molecule of H2. It would be two hydrogen atoms that are bonded together covalently. And then I would have two chlorine atoms. Now I've purposely made the chlorine gas larger than hydrogen gas because we know that hydrogen is the smallest element on the periodic table. Well, what's going to happen for this reaction to take place is that these two molecules are going to collide with each other. And if they do so, if they collide with enough force, they can break bonds and force maybe potentially new bonds to form. So, if we were to draw that, the hydrogen molecule and the chlorine molecule, if they bash into each other hard enough and with enough force, those bonds can be broken. And what can now happen is now we can get a compound of HCl formed. Now, would this be all that we would form? The answer is no. We actually would have two of these molecules form based on the conceptual picture of the collision that would occur between these two molecules. So to balance it, if I look at the conceptual application of this, there would have to be a 2 in front of here. One molecule of hydrogen colliding with one molecule of chlorine would produce 2 molecules of HCl. That would have to be true because we have to follow the law of conservation of mass. When we balance chemical equations, it is an application of the law of conservation of mass. When we balance chemical equations, we put numbers out in front of the chemical formulas. These are called coefficients. If we need only one of the molecules to balance the equation, I don't need to put a 1 in front of the compound. That is already implied. Okay? You can just leave it blank and that implies 1. But if something's other than 1, then we have to put that coefficient out in front. Okay? One other thing you might see is the state of the substances, and these tend to follow the chemical formulas. If there's an S that follows a chemical formula, that tells you that that material is a solid at room temperature. All these reactions we will assume to be run at room temperature. If not, they'll be identified as such. A G would be a gas, an L would be a liquid, and what do you think a Q would stand for? Hopefully you're thinking aqueous. So this would be an example of a solution where the chemical compound has been dissolved. More than likely, it has been dissolved in water. And because it's dissolved in water, it now has freedom to move because it's now in a solution state, and that a solid state is more likely to collide and form chemical products. Okay? So in this reaction, you might see a G after the H2 and a G after the Cl2 and a G after the HCl, which would tell us that all of these substances are gases. Okay? Some other different types of equations that you might see. The first is a word equation. A word equation transforms the chemical equation, as we see up above, into a grammatically correct sentence. So we don't say H2 collides with Cl2 to produce 2HCl. No, instead we might write the sentence as hydrogen gas, okay, reacts with chlorine gas to produce hydrogen chloride gas. That is how a chemist would speak. The word equation gives us no indication as to the chemical subscripts, the formulas, or the states of matter. Potentially they might give you states of matter, but they just tell you the chemical compounds that are the reactants and the products. You have to be able now to take those words and translate them into a skeleton equation, which is the formulas of the reactants and the products, which you can see here. This, what I've shown you, is a skeleton equation, which is often what you're going to be given for this exam. You'll be given an unbalanced, which is called the skeleton equation, which just shows you the formulas of the reactants and the products. To balance it, you then have to look at making sure the same number of atoms are on both sides of the arrow, and that ensures that the balance equation occurs. And for this, as we saw above in the conceptual application, we would need a 2 in front of the HCl. Now we end up having 2 hydrogens on the left side and 2 hydrogens on the right side, and 2 chlorines on the left side and 2 chlorines on the right side. And so the reaction is balanced, and now that's an example of what a balanced chemical equation looks like. So these are the different types of reactions or equations you might see for a chemical reaction. So one of the first things that you must be able to do to balance equations, you must be able to count atoms. Okay? When we count atoms, there is a huge difference between a coefficient and a subscript. A subscript is what will follow an element in a chemical compound, and it only applies to the element that it follows. A coefficient is out in front of the formula, and it is applied to all atoms in the compound, okay, or all atoms of the element. We don't stop applying the coefficient until we get a plus symbol or until we get an arrow, okay? So let's go ahead, and I'm going to go ahead and do this third one with you guys. It's a little bit harder. So let's, real quickly, if you want to pause the lecture already, you can. So for lithium hydroxide here, we have a 3, but that 3 gets multiplied, distributed to each of the elements. So we have 3 lithiums, 3 oxygens, and 3 hydrogens. Because there are 3 lithium hydroxide, if I had to conceptually draw it, this is what I would draw. And now counting, I would have 3 lithiums, 3 oxygens, and 3 hydrogens. So that coefficient applies to everything after it. This subscript 3 outside of the parentheses, if you have a subscript outside of parentheses, it does get distributed to everything inside of the parentheses, but what it doesn't do is it doesn't apply to the aluminum because it's not inside of the parentheses. Inside of the parentheses, the 3 only gets applied to the oxygen because that's what it follows. That 3 inside of the parentheses with the nitrate only applies to the oxygen. So 3 times 1 nitrogen is 3 nitrogens. 3 times 3 oxygens is 9 oxygens. So we have 9 more oxygens coming from the second substance, 3 coming from the first, so 3 plus 9 adds up to a total of 12 oxygens, and there is no coefficients out in front. Okay, the 3 does not apply to the aluminum because it's not inside the parentheses, and so there is just 1 aluminum. So altogether, if we were to add up all of these elements correctly, we end up getting 3 lithiums, 12 oxygens, 3 hydrogens, 1 aluminum, and 3 nitrogens. All right, real quickly, go ahead, pause the lecture, and add up the number of atoms for each of the substances identified that I just circled. All right, hopefully you got, in the first couple, they're pretty simple, 2 potassiums, 2 chlorines, 2 magnesiums, 2 oxygens. The bottom one, the key thing here is that there was oxygen in both the first element and the second element. So 2 times 4 gives me 8 oxygens with the first one, and 6 times 1 gives me 6 with the second one, for a total of 14 oxygens. The 2 out in front of the phosphate had to be multiplied to both the phosphorus, the P, and the oxygen, giving us 2 phosphoruses. Okay? And again, the 6 out in front of the sodium hydroxide is distributed and is multiplied to each of them, creating 6 of each. So again, a coefficient applies to everything after it. Okay, a subscript only applies to what immediately precedes it. Again, you're going to see plus symbols. Plus symbols separates multiple reactants and products. An arrow separates the reactants from the products. A couple other things you might see. If you see a chemical formula written over an arrow, this is a catalyst. This chemical speeds up the reaction, but is not a reactant or a product. So if I have a catalyst, and the reaction that we just did, now this is not correct. We would not need manganese dioxide to be a catalyst, but if it was present, this does not count towards the number of atoms in the reaction. It's not a reactant or a product. So if you see something over the arrow, it just indicates that it sped up the reaction, but it is not involved in any of the balancing of the chemical equation. An arrow over the arrow tells us that the reaction was heated. We had to increase the temperature of the reaction above room temperature for the reaction to occur. Some reactions don't occur unless it's several hundred degrees, several thousand degrees Celsius. If you see the word electrolysis or electricity over the arrow, this means that an electrical current was needed for the reaction to occur. And lastly, something you're not going to see much in this class, you will in AP, and this is a reversible reaction. This is a reaction that can go both forwards and backwards. We will not study this, but it'll be something that we'll do much more so for those of you that decide to take AP Chemistry. For us, we're going to really deal with single-sided reactions that when we mix the reactants, they either don't react or they do react and they go to completion. They form products. All right, so the rest of this next page is just some extra practice that I'd like you to do. I crossed off the bottom 2 on page 6 of your packet, mainly because these were reactions that you're asked to do in your homework. Instead, I replaced it with another one right here that I'd like you to do. So I'd like you to pause the lecture right now, and I'd like you to try to go through and balancing these chemical equations that I've provided. Don't do the one that I just circled. I will talk about this in a second. But I want you to go ahead and give the other few a try. And then when you restart this lecture, I will show you the answer keys, and hopefully you've got most of these correct. All right, I didn't want to show you the answer because if you were struggling, I wanted to kind of show you the steps. Okay, so one technique that students do is they'll put down each element that is present, and they will count. So if I look at just the left side, I have just an S that follows the carbon. There's only one there. There's one carbon, and there are 2 oxygens. If I look now on the right side of the arrow, there is 1 carbon and there's 2 oxygens. This tells me that the reaction, the skeleton equation, is actually the balanced equation. You do not have to put 1s out in front here. It is already implied that those are 1s. Okay? But understand that that's what it means. It's a 1, 1, 1. You need 1 of each and the reaction is balanced. Okay? Looking at the second reaction, we have hydrogen and we have oxygen. Looking at the left side of the reaction, we have 2 hydrogens and we have 2 oxygens. On the right side, we have 2 hydrogens but only 1 oxygen. So my hydrogen is balanced but not my oxygens. So what I have to do now is add a coefficient out in front to balance it. So I need to get the oxygen up to a 2. And the way I can do that is by adding a 2 or to multiply by a 2 coefficient. However, that 2 now multiplies to not only the oxygen but the hydrogen. So 2 times 2 now changes this to a 4. So now I'm no longer balanced with the hydrogens, but 2 times 1 does cause me to get and be balanced with an oxygen. But now I have 4 hydrogens on the right side. I got to get 4 hydrogens on the left side. And I can easily do that by putting a 2 here, because 2 times 2 gives me 4. And now I have 4 hydrogens on both sides, and I have 2 oxygens on both sides. Again, once the reaction is balanced, I am fulfilling the law of conservation of mass. Okay? Another technique that we can do is look at each element one at a time. So, one of the first recommendations is to always balance metals first. So I've got 1 aluminum on the left side of the arrow and 2 on the right. So immediately I got to put a 2 out in front to get the aluminums balanced. Okay? Then what I notice is I have oxygen in all 3 elements. A trick of the trade in balancing this is to leave oxygen last, because it is in the most substances. Balance all the other elements first, and usually then the oxygen will tend to be much easier to balance at the very end. So I'm going to skip over the oxygen and go right to the hydrogen. So there's 3 times 1, but then we have a 2 out in front. So literally for the hydrogen, I've got 1 times 3 with the subscript times 2 with the coefficient, which gives me 6 hydrogens. I right now have only 2 hydrogens with the water on the right side, so I need to put a 3 there. 3 times 2 gives me 6. So I still have 2 aluminums on both sides, and now I've got 6 hydrogens on both sides. Let's check the oxygen. So now with the oxygens, again, we have 1 times 3 times 2, which gives me 6. On the right side, I have 3 oxygens, and 3 times 1, 3 more, for a total of 6. By balancing the other elements, I have theoretically now balanced everything else. So this reaction is balanced as a 2-1-3. 2 aluminum hydroxides, 1 aluminum oxide, and 3 hydrogens. Okay? If you haven't done the other 2s, now pause the lecture and give it a try, and then I will show you the answers. All right. Aluminums first were 2 and 2, so I put a 2 out in front. Okay, I notice a 3 and a 2. When we have 3 and 2, the easiest way to multiply is to get to the lowest common multiple, which is 6. So I put a 2 in front, so 2 times 3 gives me 6. 3 times 2 gives me 6. And some people would stop here, but again, the 2 also applies to the aluminum. So 2 times 2 gives me 4. I got to come back and cross off the 2 and put a 4. So the final answer is 4, 3, 2 to be balanced. The last one, leave oxygen last, because oxygen is in the most substances. So 1 sodium, we're balanced. 1 nitrogen, we're balanced. 3 oxygens, 2 and 2. Now here's a trick that students that balance a lot will understand. I don't like putting a numbers out in front of here because that's going to change everything else. The key is to change the number out in front of the O2. By balancing the oxygens with the O2, I'm able to theoretically balance, okay, the reaction without changing the sodium and nitrogen. What number, and this comes down to being able to be really good with math, what number out in front of the oxygens would cause me to get there to be 3 on the left? Because right now I've got 2 and 2 more for a total of 4. I need to reduce the 2 down to a 1. How can I make O2 become 1 without changing the subscript? We can never change the subscript because it's a different chemical formula. We can't do that. If I put a 1/2 out in front of here, 1/2 times 2 gives me 1. So now I've got a total of 3 oxygens on the right side by using a fraction. It is okay to use fractions to start to balance the equation, but this is not the final answer because we can't have a fraction be the final answer. Once I've used the fraction of 1/2, what I can now do is come back and multiply the entire reaction by a coefficient to still balance the equation but get into the lowest whole number ratio. And that is we multiply all of the subscripts by the number 2 to get rid of the fraction 1/2. So 1 times 2 gives me 2, 1 times 2 gives me 2, and 1/2 times 2 gives me 1. And again, I don't even need to put it there because it's implied. So now the reaction is balanced as being 2, 2, 1. So use a fraction as a way to balance the reaction and then come back and double all of the coefficients to get it to its lowest whole number ratio. That's one of the tips or tricks that people can utilize to try to balance equations if it's difficult for you. Another one ends up being the situation that I've circled. When you see a polyatomic ion that is on both sides of the arrow and is unchanged, to balance this equation, we balance nitrate all together as one substance. I don't balance it individually as nitrogen and oxygen. It's a trick of the trade of balancing equations. So here, there are 2 nitrates on the left side, but there's only 1 nitrate on the right side. So the first thing we do is balance the polyatomic ions as whole big entities. So if I put a 2 in front of the potassium nitrate, I now have 2 nitrates on both sides of the reaction. By doing that, I've balanced both nitrogen and oxygen all at once. Okay, that gives me then 2 potassiums, so I need to put a 2 out in front of here to get 2 potassiums. Then I get 2 iodides. I've got 2 iodides, and I've got a lead, and now I'm balanced. So by balancing that nitrate first, it really makes the reaction overall balanced fairly easily by having everything balanced, by balancing it and then going to all the other single elements next. Okay? The last thing to do is to translate these word equations into formulas, create the skeleton equation, and then balance it. So go ahead and try to write the formulas of the substances here. And if you need to, you could always Google it online and get the formulas and then balance the equation. Pause the lecture and see what you get. All right, the skeleton equation. Chlorine is a diatomic element. Chlorine will always be Cl2. One note on the diatomic elements. On the chem helper, next to where it says chem is tri, I have given you the diatomic elements. Another way you can remember it, my AP students don't have that access, is something called Hofbrinkel. Hofbrinkel is an acronym that allows you to figure out that hydrogen is diatomic, oxygen is diatomic, fluorine, bromine, iodine, nitrogen, and chlorine. There are 7 diatomic elements. As an element, these guys will always exist as 2 atoms bonded together. Any other element, if I say zinc reacts with something, iron reacts with something, iron is just simply Fe. All of the other elements are monatomic. Carbon, sulfur. Okay? These are single elements. But if it's one of the 7 elements on the periodic table as identified as diatomic, you must always write them as diatomic. So iodine and chlorine are diatomic elements. Potassium iodide and potassium chloride are ionic compounds. We don't see prefixes in their name, so we'd have to look at charges, and you should get the formula of Ki and KCl. So right here is the skeleton equation. So this is where we translate the word equation to the skeleton, and now we balance. I've got 2 chlorines on the left. I only have 1 on the right, so I need to put a 2 here. That gives me 2 potassiums, so I need to put a 2 in front of the potassium. That also gives me 2 iodines, and now the reaction is balanced. So hopefully you wrote Cl2 plus 2 Ki produces 2 KCl and I2. One thing I did also put down is the state of matter. They told me the iodine and the chlorine were gases. They didn't tell me what the potassium iodide and potassium chloride are. But if something is ionically bonded, ionic compounds tend to be solids at very high temperatures even. So usually if you're asked to predict, it'd be a solid. That is something you're not going to be expected to do in the test. So understand that if they don't ask for states of matter, you don't have to really worry about putting them down. Okay? All right, if you want to pause the lecture for one last time, I will translate the last three word equations and see what you get. All right, here are the final answers. Copper 2 carbonate produces carbon dioxide and copper 2 oxide. This reaction, if you have the right formulas, is already balanced as a skeleton. We just have one of each. Iron is a solid, chlorine is a gas, produces iron chloride. The subscript coefficients are 2, 3, and 2. Again, chlorine is a diatomic element, iron is not. And then lastly, carbon and sulfur are both not diatomic elements, forming carbon disulfide, CS2. And all of them are solids at room temperature, and we just need a 2 in front of the sulfur to balance, and right there is the answer. So that's how we do balancing equations and how to translate word equations into a skeleton equation and then balance it are the steps in balancing equations. So now it's just a matter of you getting lots of practice at doing these. So the first practice I'd like you to do is to do pages 7. I'm also going to supply you additional practice problems and also have interactive websites that you can log into to get further practice in balancing equations. But do a bunch of practice on this. You're going to start to develop different techniques and how to balance equations very quickly and efficiently, and that will hopefully make this test be an easy one for you to get a very good grade on. Again, thanks for listening. And 8 in your packet, and I will supply you the answer key online. But go ahead, give it a practice.